Good morning, everyone, and welcome to this online meetup. This is pretty new for many of us, I guess, given the situation. Thanks for joining here. And I am Arun Tyagarajan. I work for the network engineering team in LinkedIn. And in this talk, I'm going to be joined along with by Saira and Kumar, who work for the software engineering team. And we are going to cover about how LinkedIn moved it to a unified fabric in the data center and how distributed firewall played a role in that. So before I jump into the specifics of the talk, I just want to give you some background, like what we call the fabric and how that plays a role in the data center. Sarah, can you move to the next slide? Thanks. So what is the network fabric we mean? Network fabric is something like this is the underlying infrastructure in any data center, wherein like all the hosts which are part of the data center get somewhere interconnected through, and it helps to set up the communication flows between multiple servers, right? So for those of you who are not much of the network background, so these are kind of the switching layers which are in multiple stages. We call it like the closed network, where the host connect to the access layer and then they aggregate at the spine layer and then the super spine. And this kind of architecture is what pretty much followed in most of the highly scalable data centers, even be it like the cloud providers or uh, very large enterprises like LinkedIn. So this layer provides for higher capacity of bandwidth exchanges between different pods, and also at times it also serves as the point of enforcing security rules between different environments. When I say different environments, I refer to environments something like the production environment, the staging, the tooling infrastructures, and so on and so forth, right? So this layer is kind of so far built with a confinement of the security domains. There are certain security domains which cannot overextend to other security domains for various reasons, right? You don't want your staging infrastructure directly interfacing with most of the prod environment, maybe some, right? And similarly, your office network don't want to directly connect to the production environment, right? So there are a lot of security rules there, and there are some legitimate security rules as well required. So these are enforced at this fabric layer. And there are separate fabric built for each of this environment so that we are able to scale to thousands of servers inside a data center. And also sometimes even some of the environments have kind of multiple thousands of servers as well. So this plays a key role in how your data center is built. But when you look at this approach, though it helps you to scale to a level, but when you want to have massive scales like LinkedIn, like you want to have 100,000 servers in a data center or more, then these introduce some limitations on how we grow, right? Um, can you move on to the next slide, Sarah? So what are the challenges? Like when you have partitions of fabric built, you are not in a position to grow at a rapid scale because like your capacity planning exercise is going to be limited to what that each of these partitions are going to need, right? And there will be certain partitions which will be highly utilized. There will be certain partitions which may not be utilized. Still, you will be investing and deploying resources just to comply with your standard capacity planning process, right? And so we wanted to break away from this approach where we want to maximize the resource utilization because like as we are adding thousands of servers quarter on quarter, we need to be mindful of how we are utilizing them and we are making most of it. So, so the thought process was to move towards something called as the unified fabric, where we can pull together all these resources together and share the environment across the different services and the applications which need them, right? So when you integrate this, all these partitions together, you are able to uh, uh, rapidly expand the capacity irrespective of where these requirements are coming from, and also you'll be able to improve the efficiency of resource utilization, right? And breaking away from the physical boundaries also helps you to simplify your network operations and also your infrastructure operations, because you have a unified fabric, and uh, you're not going to have certain customizations or kind of variations from the standard deployments for each of the partitions. So it saves a lot of overhead from the way you build the environment and also how you operate them, right? And also it helps you to gain the service mobility. You are not confined within your partition, right? You will be able to uh, pick a server or pick resources where it is unused in any part of the data center, and you'll be able to leverage them for your capacity expansion or even to um, uh, improve your resiliency. Like there are applications which need maximum resiliency, like rack level resiliency or even suite level resiliency. So you are kind of untied from a lot of these restrictions, and you are free to build the network or the services the way you want, right? And one of the other advantages, like since you build a unified fabric, you are not in a position to have a security rule at the core layer of the network, right? You have some high scale firewalls or routers with access list, which have finite TCAM resources, which cannot allow you to go beyond a limit. So when you're talking about 100,000 servers or more, and you have very granular controls on security rules, you are kind of limited by the how these hardwares are going to be supported, and also these are very expensive resources for you to keep expanding them horizontally. So the thought process here was to like decouple them these together, like leave the switching fabric only for traffic forwarding and move most of the security rules to the end host from where the communications are initiated. So when you move the security rules down the layer in the network fabric, the point of interswitching the traffic, like mainly the east-west traffic, gets done at a much lower layer, which means you are saving on the number of hops you're traversing. You don't have to go all the way to the central firewall or a central access control point to cross to different environment. So as your latency improves, like due to number of hops getting reduced, the east-west communication kind of gets better. The throughputs get better, and also you don't you don't have to queue the traffic at the switches. So this kind of summed up to an overall like win-win situation where like we'll be able to leverage most of the resources much efficiently, as well as the end services and the application see improvements in the way the infrastructure is working, right? So this is where we intended to build something called as the one big fabric. Sarah, can you move to the next slide? Yes. So the one big fabric, this is like a very hypothetical or a very 1,000 feet or 10,000 feet level view of how this looks like. So now if you see that major part of the data center are kind of considered as a single switching fabric, where you build multiple pods as per your capacity needs are or capacity projections are, and you plug all of them together into a common switching fabric, and you open up this infrastructure for the service owners to go and allocate resources for how many resources they need based on the resiliency requirement, the capacity requirement, and also the performance requirement. So in this approach, what happens is like you have good amount of your infrastructure sharing the same the switching layer, and also what happens is like the traffic flow between them also within the stays within the fabric. You don't have to go through the physical firewalls uh, or any of them, so that it allows you to scale at 100 gigs, 25 gigs, or yeah, even more than that. All right. So this is how a network looks like, but not everything is going to align with this flat network, because there are certain environments or special use cases which cannot have a flat network, right? Something like you have hosts which are talking to the external environment, like you have your mail servers or you have your proxies or certain host which doesn't can't support firewalling at their service layer or at the host layer. right? Certain OSs has some limitations or feature incompatibilities there where it doesn't fit into the larger definitions of how the security rules have to be enforced. So for the special use cases, we build something as special pods, which are going to go behind a physical firewall, where we specify the rules on the firewalls. So this is pretty much like the traditional way of doing it. But the majority of the use cases are going to be served using this one big fabric. So, and this is where majority of the services and the expansion happen. So it kinds of solve the larger problem what we have, right? So as part of this, building this, so what are the key components here? Like how do we go towards like from the traditional approach to this, right? So when you go for this kind of a solution, you need to have switching fabric which are of massive capacity, because like you're building a flat network, your application can be spread across n number of pods, and you don't have pretty much control over like which pods or where exactly they are going to get deployed. So you need to be mindful of having enough infrastructure capacity to support any kind of deployment. So we had to move towards switching fabric which are of higher capacity, like we moved towards 100 gigs and now we are moving towards 400 gig capacity. And also we need to be careful about what kind of platforms we are going to choose, because we are going to uh, make a network which supports all kind of traffic flows, which can be like some can be busty traffic flows, some can be non-busty traffic flows. This is going to impact the way your queues are used in the switching layer, and the platforms which we have to pick for this kind of switching fabric is going to be specific towards those needs. So so we have to be mindful about how the switching layer is designed and what platforms are used. And also the other component is the security component, where like you want to have this all those rules enforced at the host layer, but you need to have a centralized control over like how these rules are defined and how these rules are propagated to the host, so that we are always aligned to what the security the permissions are. You don't want any deviations from that. So there are many components in this which makes this solution work. And today's talk is more focused about the one part, the security part, of how DFW is going to help you to implement this security. And I would like to ask Saira to come and present on the DFW solution.
Thank you, Arun. So, Arun briefly explained the idea behind single fabric. And one of the major enablers of single fabric is distributed firewall, or as we call DFW. Yeah. So, what is distributed firewall? It's a LinkedIn homegrown software firewall solution. It provides security at the host level and can run on any server that comes with NetFiddler kernel modules. As the security rules are now enforced at the host level, this gives us the flexibility to define the rules at much more granular level and also customize these rules to fit the application requirements. And one of the thing DFW also does is managing this host level packet logging and provided centrally for auditing purpose. Yeah. So why did we go about building a in-house solution as opposed to leveraging something that's already existing? Well, I'll go about talking some of the requirements that were very important to us, and there was no one solution that could provide all of these. So the first and foremost being security. Uh, we wanted to make sure LinkedIn's infra is always protected even when the systems fail. So that was the most important requirement we had. Next, logging and auditing. So we wanted DFW to capture all of the logging events and make it available at central place. So even when there is a security incident at a single host level, we should be easily identify it with these logs present at one place. And next is the fast rule updates. our environment is constantly changing. There are services deployed always, and before instance come online and begin to serve traffic, we would like to make sure all of the security rules are in place to avoid any service impact to the application. uh, the next one is standard tooling. So most of the LinkedIn tooling are built in-house. We wanted DFW to understand these terminologies and seamlessly integrate into our standard tooling ecosystem. And we have thousands of services, and these services run, some run on container environments, some run on bare metal, some run on VMs. No matter what kind of environment our application runs, we would want DFW to make sure it always provides the security the application needs. So having learned about the design drivers, let's dive into the architecture part of it. As you can see, DFW follows client-server architecture. At the bottom, we have these agents. So these agents run on every single server in LinkedIn's data center. The primary responsibility of these agents is to ensure the rules are always enforced. And these rules come from DFWDB, which is the core to our architecture. The job of DFWDB is to generate these rules for all of the agents and also make sure they are distributed in a timely manner. But DFW cannot generate these rules on its own. Uh, it contacts some of the source of truths like ACLDB, which is our data store for network ACLs. And another source of truth we have is topology, or in simple terms, service catalog, which kind of give us an information about, given a service, what are the list of instances or hosts that participate to serve the traffic. So yeah, so DB polls these source of truth at regular interval of time, downloads the rule, generates them, and distribute to the agent. Uh, we also have Kafka sitting there. So that is primarily used for two purposes: for listening to environmental change events, and also to forward or publish the log events from the agents to a centralized place. So uh, you see there are multiple instances of DB here, but an agent can connect to only one DB at a time. So the way all of the agents are aware of all of the DB instances, uh, they run a hashing algorithm to decide which primary server they would connect to, and once they are connected, they make sure a persistent connection to listen to any rule update events. In the event one of the DB instances goes down, the agents are clever enough to move to the next healthy instance of the DB. And when the agent, when the DB instance is back online, the agent will connect back to its primary server. So all this happened via heartbeats. DB send heartbeat to the agent, and agent send heartbeat to the DBs. So this is the high level architecture of DFW. Yeah. Uh, Throughout this project, we came across some of the scaling or design challenges. While this is not an exhaustive list, these are some of the top of the minds which we want to discuss. So let's go over one by one. Yeah, the first one is minimizing rule notification. So uh, in our first iteration of our DFW, all of the rule change notification were broadcasted to every single agent in the data center. Uh, this was not required because a DB instance is responsible to cater to those agents that are connected to it. So this was one challenge, and the the challenge was actually when there is a rule change, because we have thousands of rule and thousands of agents listening, this will lead to millions of messages per minute to be sent. So to fix this issue, we decided we would track the agents that are connected actively and do the broadcast only to these agents which are connected to a given instance. Uh, and this was done via heartbeat, where both DB sends its heartbeat to the agent and agent sends its heartbeat to the DB. Another improvement we did was reducing the payload size of the message. So at a very high level, we could classify the rules, the messages into uh, different categories. They are heartbeat events, they are log events, they are rule notification events. So we decided on a standard message format, and each of the message carries a different payload, and if the payload is bigger, the data does not go as part of the notification. So let's see this via a diagram. So yeah, so DB send their heartbeat to all of the boxes. Similarly, all of the agents send the heartbeat to the DB. So there is no filtering here because the heartbeat is a must in both the direction. But let's look at a rule set a notification. So in this case, this time the type of message was data type, and it has information about production rule set. So although we broadcasted it, only the hosts that were labeled as prod accepted those requests. So similarly, we have logs going on to the DB, and again, host related data, zone related data, and so on. Yeah. So the next challenge was reducing the load on Kafka and DFWDB. So one of the requirements of DB was to make the packet logs and other firewall related logs to be available centrally. Our initial thought was having the agents publish these log messages to the Kafka, but imagine the scale at which LinkedIn runs. So thousands of server publishing to same topic is not a feasible solution. And moreover, these log messages are string based. We the consumers of the Kafka expect these to be in a well uh, uh, formatted message where it conforms to a schema. So how do we fix this challenge? So our first approach was to distribute the translation of this string-based log messages into a JSON format to the agents. So now the agent themselves translate these log messages to the well formatted messages which can be readily consumed by the downstream application. And then instead of having these agents published directly to the Kafka topic, these will be forwarded to the DB instance the agents are connected to. And the job of the DB is now simplified. It groups different type of the messages and forwards them to the specific Kafka topic. So the load of parsing the log messages and getting into a format that is consumable by the downstream application was distributed to the agent. And the instead of having all of the agents connect to Kafka, now our DB instances do the job on behalf of the agents. So yeah, the next challenge was fast rule propagation. Like I said before, we have thousands of services. There are constant deployment happening, and in this changing environment, uh, even before a instance come online and begin to serve the traffic, it should have all the necessary rules. If you remember, I said our DB instances poll the source of truth. and that happen at a regular interval of time. And if we rely on that kind of a system, then there's going to be always delay from the time when the rule was created and to the time when it was actually enforced on the host. And this time is good enough to cause an impact to the services. So we had to tweak our design to accommodate fast rule propagation. So the way we did it was, yeah. So this topology will publish the deployment events to the Kafka, and now the DB not just listens to the source of truth like ACL-DB, it also listens to the deployment events. And when there is an event, DB quickly pulls the instances that have gone through a change, generate the rules, and let the agents know that they need to update their rules, and the agent will quickly download those rules and apply on the box. And all these happen at such in less than a minute time, and even before the instance is ready to serve the traffic. So that's how we solve the problem of fast rule propagation. So yeah, I would like to hand over to Kumar to go over the rollout challenges and enforcement challenges we had. So over to you, Kumar.
Thank you, Saira. Arun and Saira have walked us through the one-way fabric and how GFW enables OBF, right? So in the next few slides, I'll be walking through you to the other challenges that we faced. So with the huge number of servers that LinkedIn operates, one of the biggest challenges, how do we roll out things at scale, right? So there are a lot of challenges that we have faced, out of which few of them I have listed below. So there is, how do we tackle with zero downtime, and how do we tackle with high number of applications to server ratio in places like LinkedIn corporate network, and how did we tackle with priority conflicts, and how do we tackle the data quality, right? Sarah, can you move on to the next slide? Yeah, thank you. So the first one is zero downtime rollout. In our infrastructure, there are a lot of critical applications that are running on the servers, and we are dealing with firewalls and ACLs, right? So if we don't roll out cleanly, we would start dropping the packets, which will basically cause an outage to the application. So in order to tackle this, so what we have done is three-phase rollout, so that there is no downtime and no impact on the applications that are running. So as you see in the response side, there are three phases. First one is logging only phase, where as the name is implying, it's just log the packets. So there is no action taken on these packets. In this phase, however, so whenever a packet comes to the server, we just pass we just pass through the ACL rules, and then at the end of the rules, we log whether we accept the packet or we reject the packet. Even if the packet has to be rejected, we just log that it has been rejected and then just pass on to the kernel, right? So in this phase, we'll be able to know whether the packet is getting accepted or rejecting, but we are not actually rejecting the packet. And the next phase is auditing phase. We can think this as a baking phase, where we analyze the logs in the previous phase and determine whether basically the packets which are coming through are legitimate or not. If the packets are legitimate and then they're dropping, we create the necessary ACLs for them, and if they are not legitimate, we just leave it. We just leave the packets as it is. So by the end of the second phase, we must be sure that there are no legitimate packets that are getting robbed. And the last one is the enforcing phase, where we start to enforce the approved ACLs. Here we start or drop the packets that are not having the necessary ACLs. So by this three-phase rollout, we made sure that there is no impact on applications that are running, and there is no zero downtime for them. Yeah. Next slide. Yeah. So the next challenge is high application to server ratio in places like corporate networks, mainly which are not serving the user traffic. It's basically applications which are running inside the LinkedIn infrastructure, right? Yeah, with the scale that LinkedIn operates, there are a lot of applications running, and they're all different. And then none, no, like one of the application can be matched to other application. Like for an example, uh, an application will be based on containers, and some of them will be on running on bare metals, and so on. So we had to design DFW differently for each of the application, so that there is no impact when we roll out on them. So what we had to do here is we had to coordinate with the application owners and have working sessions with them, um, so that they understand the application and then roll out with, and we can roll out with their specific solution for them. Yeah, next slide, Sarah. Yeah. And then other challenge that we faced is priority conflicts. So as I say, when we roll out, we need to coordinate with a lot of teams and get their involvement while we roll out, right? So as any team will be having their own conflicts, and then their own uh, applications, and then they have their own priorities, right? So getting their involvement is tough. So when what we had done is to match our timelines with them, and then we had to escalate it to a senior leadership on the onboarding team, and get a dedicated resource uh, for the commitment and from his timelines while we are rolling out. Next slide. Yeah. And the last challenge in the rollout is while we are rolling out is data quality. Like, how do we differentiate a host which is supposed to run DFW and which is not supposed to run DFW? Like, for example, the Solaris hope boxes or DB boxes which are serving traffic might not run DFW because they don't have the kernel functionalities which support the firewall rules, right? So how do we differentiate these kind of hosts from which are supposed to run DFW, right? And how did we deal with this? We introduced a new labeling to each of the hosts that are in the data center, which you can think of like a Boolean value, which actually differentiates the host that is supposed to run DFW and that is not supposed to run DFW. Yeah. Next slide. Yeah. Until now, we have gone through the rollout challenges. What are the challenges that we faced while you're rolling out, right? So the next set of challenges that we have come across and can be categorized as enforcement challenges. So what are the challenges that we faced while we started to enforce the rules on the servers? So the next few slides, I'll be walking through the challenges while we are enforcing. Yeah. Next slide. Yeah. So the first one being unknown port access. So while we are in the auditing phase, we have seen some undocumented port access, like some ports which we don't know, like there is some traffic flowing to that server on that port. And as we know that there is no lack of ownership on them, because of which our rollouts has been slowed down and so on. So what we had done is to, in this situation, is to trace out the SMEs and vendor documentations uh, for each of the unknown port access, and then ask them to weed out undocumented posts or raise necessary ACLs. Yeah, yeah. So the next challenge is security requirements. So as by now you would have understand that DFW itself will be running as an application on each server. So when you run as an application on each server, there would be some unknown issues which might not come across in day-to-day life, and which would cause GFW to fail, and which indirectly fails to enforce the rules on the server. So by failing rules, by not enforcing the rules on the server, is a security outage in an instant, right? So what we had done in this case is to follow a strong process for each incident response with very clearly defined SOPs. As you see in the response column, we follow a process which is known as scan, detect, and remediate system, which deals with all the kinds of security issues like any failed open where the host is open to a security issue, right? So the first one is scan, where we continually scan the entire LinkedIn data center, crisscross across every other environments, and then where we detect that a host is failing to enforce the rules. We try to fix, once we detect that the host is open, we have an auto remediation system in places which try to fix DFW on the host by inserting rules, static rules and dynamic rules and so and so. And if we cannot repair this host after the auto remediation step, then we move the host to a quarantine state where the host is not accessible to the other environments and the host is not open anymore. Next slide. Yeah. The last challenge being the host-based changes. As you guys might be knowing, right? Data center is never constant. There will be regular reboots, new system that get discovered in the network. There will be new builds, and then there will be host gets reimaged, and so and so. How do we enforce that the security is not compromised while there are state changes in the host, right? So on the right side, there is a life cycle diagram of a server where you can see what is the life cycle of a server, right? Yeah. So on the as you see, the ones that are colored in the blue section, where we strictly enforce the rules so that the security is not compromised. So after the host is racked up and it gets discovered in the network, we start off by fencing some host-based, kickstart IP table rules, right? So when the host transits to an install state, and it is in running state, we run DFW as an application on the server, which would enforce the rules on them. And during reboots, we enforce the rules by right ordering of network processors and DFW on each host. So by this kickstart based on IP tables and right network ordering, we enforce that the host is never compromised to security and never open in the data center. Next slide. Yeah. As a whole, this is our journey and the different challenges that we have gone through the phase of making our data center into a single fabric. Now we'll move on to the most valuable part of the talk. We are ready to take any questions if you have.
Hey, thanks a lot, Kumar, Shaira, and Arun for the talk. So we have one question in the Q&A section. The question is from Vijay. In this architecture, how do you apply different rules to two systems of two machines? Are you applying all rules to all systems or filtering somewhere?
Okay, I can take that question. So the rules on different system are different. The way I would like to answer this is, for a given application, the rule set would be same because they would listen on similar ports. They are in a similar security domain. But yeah, different application will have different set of rules. But for a particular application, the rule set is almost similar. Except for the cases where we want to enforce much stricter rules, and there are some special cases in which case the host within an application might also have a different set of rules.
Cool, then. That is the end of the first talk then. Thanks a lot, Sarah, Kamal, and Arun for that wonderful talk.